Hello and welcome to the AI Research Roundup. I'm your host Alex, and it's great to have you with us as we explore the latest in AI research. Today we're diving into a paper called MultiMed, Multilingual Medical Speech Recognition via Attention Encoder Decoder. This paper tackles a really important area automatic speech recognition, or ASR, specifically for the medical field. The authors introduce MultiMed, which they describe as the first multilingual medical ASR dataset and model collection spanning 5 languages, including English, German, and Mandarin. It aims to improve things like communication and diagnoses in healthcare settings. Now, part of their work involved evaluating different models and training approaches. This first table gives us a look at the models they use, specifically the whisper models, and how many parameters needed training depending on the method. You can see they tested 4 sizes, tiny base, small, and medium. And they looked at 2 ways to fine-tune them, fully fine-tuning everything, or just fine-tuning the decoder part. Naturally, fully fine-tuning involves more parameters. For instance, the medium model has about 764 million parameters when fully fine-tuned, but only around 457 million when just the decoder is trained. Well, this difference is important because fewer trainable parameters often means faster training and less computational cost. Okay, so we saw the different model sizes and how many parameters were involved, depending on whether you fine-tuned everything or just the decoder. This next table, Table 2, shows the actual performance results specifically for that decoder-only fine-tuning approach, where the encoder was kept frozen. It breaks down the word error rate, or WER, and character error rate, CER, for each language. Vietnamese, English, French, German, and Chinese, across those 4 whisper model sizes, tiny base, small, and medium. Generally speaking, the results get better as the model size increases. So lower error rates, which is good. For instance, looking at the test set for English, the medium model achieved a WER of about 19.4%, compared to nearly 30% for the tiny model. The medium model actually gave the best WER for most languages here, like Vietnamese, English, and French. Interestingly, for Chinese CER, the small model did slightly better. So it seems bigger models generally help, but there might be some language-specific differences too. Right, so that was decoder-only fine-tuning. Now this next table, Table 3, shows the results for the other approach, fully encoder-decoder fine-tuning. This means all the parameters in both the encoder and decoder parts of the whisper models were trained. Again, we see the WER and CER across the 5 languages and 4 model sizes. Similar to before, the larger models generally give lower error rates. Looking at the test set results for German, for example, the medium model achieved a WER of about 24.1% compared to over 31% for the tiny model. While this full fine-tuning often improves results slightly compared to just tuning the decoder, but remember from Table 1, it also requires training many more parameters. Okay, so we've looked at the different ways to fine-tune the whisper models, which are a type of attention encoder decoder, or AED model. This next table, Table 5, shifts gears a bit and compares those AED models, specifically the small and medium whisper ones, against a different approach called hybrid ASR models. This comparison is done just on the Vietnamese dataset. What's really interesting here is the performance. The hybrid models, specifically XLSR53 Viet, achieved a word error rate of 28.8% on the test set, which is exactly the same as the small whisper model. And the W2V2 Viet hybrid model was very close at 29.0%. Well, this is notable because if you look at the parameters, the hybrid models have fewer parameters, about 123 million, compared to 153 million for the small whisper. They were also pre-trained on much less labeled data. So, it suggests these hybrid models can be quite efficient, achieving similar results with less data and fewer parameters, although the much larger medium whisper model still got the best score overall at 25.4% WER. Okay, so we just saw how hybrid models stack up against the whisper AED models for Vietnamese. Another strategy the researchers tested was multilingual fine-tuning, basically training a single model on all the languages together. This table 4, shows the results for that approach using the small whisper model with full fine-tuning. Well, interestingly, this actually improved performance for most languages like English, German, and even Vietnamese compared to training them individually. For example, English test WER dropped to about 16.6%, but Chinese performance really suffered here with a WER over 100%. So multilingual training seems beneficial in many cases, but not universally. Right, so multilingual training can help for some languages, but might hurt others, like Chinese. The researchers also wanted to understand how exactly fine-tuning works best, specifically which parts of the model benefit most from being trained. This table 6, shows an ablation study using the small whisper model. They tried freezing different combinations of layers in the encoder and the decoder during monolingual training. For example, freezing the first 9 layers of the encoder, or maybe the last few layers of the decoder. Well, the results showed that these choices matter. While fully fine-tuning everything often gives good results, as we saw in Table 3, freezing, the entire encoder, which we looked at in Table 2, is also quite effective and computationally cheaper. This table suggests that getting fancy with freezing only parts of the encoder or non-consecutive layers in the decoder doesn't necessarily help and can sometimes lead to worse performance, particularly for languages like French or Chinese in some configurations here. So it reinforces that careful consideration of the fine-tuning strategy is needed. Okay, besides the fine-tuning strategy itself, how the data is prepared can also make a difference. This figure 1, looks at exactly that for the German language data. It compares the performance of the Whisper small and medium models when trained on 2 different types of audio segments. One type is the original short audio clips, and the other is where these short clips were concatenated or joined together into longer segments of up to about 15 seconds. Well, the results are pretty clear from the bar charts. For both the small and medium models, the word error rate, or WER, is much lower when using the concatenated segments compared to the short ones. So, this suggests that preparing the data by concatenating shorter audio files into longer ones really helps improve the transcription accuracy for German medical speech. So yeah, that data concatenation trick really seemed to boost the German results quite a bit. Looking at the bigger picture though, this MultiMed paper really shows a promising direction for handling medical speech across different languages. It highlights how, well, not just the core model, but also careful fine-tuning and data strategies are super important, especially for specialized areas like this. Work like this is vital for making AI truly practical and helpful in healthcare globally. That's all for this episode. Thanks for tuning in. I'm Alex, host of the AI Research Roundup.